Hello, Flat Earth researchers, debaters, and debunkers. Photographs like this one here, where we see the sun setting, I presume, are often held up as absolute proof that we live on the outside of a spinning globe. But these pictures and those assumptions are merely proof that we have been conditioned to interpret what we see in reality in order to fit a desired model that was created hundreds of years ago by Copernicus that didn't have any basis in reality. The only reason that it is assumed the Earth is another planet going around the Sun is because this assumption was made that the Sun is static and at the center of our known universe or the solar system. And so, of course, in order to model night and day on an Earth that is going around a central sun, we have to make the Earth a sphere. And so this is what we imagine is happening when we see a sunrise and a sunset. But we really don't put too much thought into it, do we, most of the time? So what we're going to do in this video is have a look at reality and what really happens to horizons when we observe them in reality, and compare that to a curvature calculator to see that the curvature calculator has absolutely no basis in reality. It doesn't represent what we see in reality whatsoever. But before we do that, let's just look at what we see and would usually assume from a photograph like this, where we see the sun in the distance being cut off by the horizon. Now, it does look like an edge, doesn't it? The horizon, when we are low to the surface, has this very clearly defined line. It's a very sharp line that really does look like an edge. And so it's funny how we can then have these stories told to us when we're younger that, oh, in the olden days, before we had science to help us out, people used to believe that you would sail off the edge of the earth if you got to the horizon. But of course we know it's not an edge, but equally so, this line that we see here is not the beginning of any curvature. Now it's not a bulge, is it? Water doesn't bulge up in front of us. That is sometimes how it might be represented with orthographic views or a side-on view of what we're seeing. But no, it's neither a bulge nor an edge, and nor is it the beginning of any curvature. The horizon is actually an indicator of our height above the surface. And it always tells us, especially when we look at what else is going on in the picture, in the foreground or in the background in relation to our height. So, of course, it's assumed that the horizon is something that has a fixed form or shape or contour, a curve. It's supposed to be a continuous curve. Of course, we never see a continuous curve anywhere. There's explanations that we, the higher up we go, the further down we have to look to this alleged curve. So let's have a look at how that is represented in the diagrams on a curvature calculator. So here we're looking at the forum on this metabunk.org website run by Mick West, who's very much an anti-flat earther and has done a lot to try and promote the belief in the globe. And he refers to this curvature calculator here. Now, it's interesting to point out what's actually being said here. That the Metabunk curve calculator was written to provide a simple answer to the question, how much of a distant object is hidden by the curve of the Earth from a certain distance and view position. The following diagram is an exaggerated look at the numbers involved. Okay, so we can go and have a look at that. But the focus, remember, has always been on the bottom of something on the surface of the Earth being cut off, depending on your height above the surface. So here's the curvature calculator that he was referring to. And here we have the eye, camera, and the viewer height. So you can adjust that on this calculator, up and down. And you can see here that we have eye level. So in this sense, the word eye level is basically meant to refer to the viewer height. It's the same thing, but it's a horizontal line. So yes, you can talk about eye level in a number of different ways. In these models, eye level is often meant to mean the height above the surface, and it doesn't necessarily matter which way that person is looking. But if they looked out horizontally, then their horizontal line of sight would be along this eye level. So often I refer to eye level as that looking straight ahead in a horizontal line that would be perpendicular to your plumb or your vertical, which is what it is. You have this horizontal line and it's perpendicular to the vertical here, regardless of the shape of the Earth or any assumptions of what is beneath your feet. Your eye level is simply the direct, you're looking out at that height, yes, but you're looking also, if you're looking in the eye level direction, then it is this horizontal line of sight. Now, what happens here is as you raise your eye level up and down, then the horizon, of course, gets closer to you as you get closer to the surface, and the horizon gets further away as you gain more height above the surface. Now, in this sense, that is a somewhat true representation of what happens when we look across the surface of the Earth, or any level surface that goes off into the distance, is that the higher we get, the further we can see it with clarity and certain detail across the surface, until there's a limit where everything on the surface appears to get very much more condensed. But the main problem here is that this is a total misrepresentation of what we actually see. We do not in any way ever look down towards the horizon. And what we do in fact see when we look across the Earth is the horizon appearing to be at the same height as our eye level. And that's simply because of the way perspective works. And perspective can be described in terms of geometry. So what we have here is geometry being used. Now, the model can prove itself. All of these things can be adjusted, and your model works. It is a so-called working model, and you can accurately calculate or measure, if you like, the distances and the angles that occur when we make these changes to the observer's height. So what we have here in this model is an assumption that the Earth's surface is fixed. It's a fixed geometric shape. It's static. It doesn't move. We are the ones moving, okay? This is very important to keep in mind. This model requires and assumes that the surface is curved, and it curves down and away from us, wherever the observer might be. You can stick the observer anywhere on this circle to represent an assumed side-on view of what the observer is seeing or doing. We never actually see this ourselves, do we? This is this is an interpretation. And so we have geometry used to create the circles, and we have the angles here with the height and the tangent lines, all these other things, and it's fixed. And of course, if you're modeling something like this, you can assume any measurements you want. You can make any radius you want. You can make these miles, inches, millimeters, anything. It doesn't matter, and it will always be the same. The model will always work when you move these things up and down, and you get your angles, and so it all appears to work. But again, the important thing to keep in mind here is that we have geometry used, but also perspective, the way we see the world around us, can also be described using geometry. So what we have here is ignorance, or an interpretation of the geometry that can be used to describe how we see the world through our spherical eyes, and then it's been flipped into this model. So as I said, it is indeed true that you gain height above the surface of the Earth. You do indeed see further with much more clarity. And the lower you go, the more things will get cut off as you get... anything on the surface will get cut off. So as you bring this observer height down, you get a horizon that comes a lot closer. And this is just to do with, again, perspective and the angles of resolution. And, there's a limit to how far we can see clearly across the surface. And then everything beyond that is just part of the horizon, or is obscured by whatever is in front of us. So, of course, if we are low to the surface, then something very small on the surface will disrupt our view. Of course, we've got issues with angular size. For example, the lower you get to the surface, the more a small wave in front of you on the surface of the water is going to disrupt your view of something much further away, and of course apparently much smaller in angular size because it's further away. So a tiny ship on the horizon will indeed be easily obscured by a wave that's a couple of feet high if you're very close to the surface. Now again, remember, these models are based on very smooth lines, but you don't get that in nature. There is no natural surface in nature that is completely smooth. Yeah, they've all got dips and bumps, and they're all rugged, and the sea especially is moving all the time. And of course there's temperature fluctuations, and then people start arguing about refraction and all these kinds of things. But essentially they're missing the point. This is a totally false representation of what we see or how we look at the Earth. Okay, it works as a model, fine. You draw these lines and you've got angles, and they all work in of itself. You can prove the model just by doing that, but it doesn't prove that that's what's happening in reality. And of course the focus is here on what's hidden. Nothing else, just what's hidden. So yes, as we said, something will get hidden because it's on a choppy or rugged surface, and it's much, much smaller in our vision than it would be if it was as close as whatever is on the surface. And it's not just one thing on the surface. There are many things. If it's water or a salt flat even, there's still going to be things on the surface which disrupt the view. Okay? Fixed geometric surface and the observer moving. That's the model. And we're told that that's where the horizon appears, and we have to look down to it, and there's a horizon dip. There is no talk of looking at eye level. So let's go and look at how things actually appear in reality. First, let's take a look at this lovely picture I found floating around on the web. you might look at this photograph and immediately point out the curved looking horizon. And you would say, there you go, flat Earth debunked. We've got evidence of curvature here. Is this what we really see in reality? Have a little think about this when we are looking in one particular direction and our field of view is, I can't remember exactly how many degrees our field of view would be here. But then if you say that we are seeing a bulge or a bend here, let's have a look. Can you see that? There is a bend if you compare it to the straight horizontal line, but you say, well, there you go, there's your curvature. There's your side-to-side curvature. So, okay, let's suppose that we turn around 180 degrees, we face the opposite direction, and we're on top of a mountain or an island or something, and we've got a similar view when we turn around. And we take another picture, and we get the same results. We get this apparent bulge of curvature right in the middle of our field of view, and then the sides going down left to right here. Well, what does that do to the original picture? If we have the same bulge in front of us looking in both directions, and then we have this sloping off or curving off down on the left and right, well, those two pictures, or if you did then you put those together as a 360 degree view as you turned around, then no, we don't see these petals of curvature in front of us. This is just because we're looking through a wide angle lens. So this has indeed distorted reality to a certain extent. It's probably a wide angle lens, and even the most expensive wide angle lenses will create this bend in the horizon. So it's a ridiculous argument. There is no left to right curvature, just as there is no curvature beyond the horizon as far as we can see. And even if you do make this claim that you can see a bend on either side of this photograph, which we can indeed see, then of course that's not going to just doesn't fit together as a seamless 360 degree picture, does it? I'm sure you can imagine that. Flat earthers are often accused of not being able to think in 3D. Well, all I'm asking you to do is think about the results if you took a picture in the opposite direction, and you would see the same thing. But that doesn't fit with what's actually happening in reality, because it's an optical effect based on the lens that we're looking through. If you had a concave lens, then we'd have this kind of more pinching effect. Everything would look pinched rather than bulging. It's just an artifact of the lens. But one thing we can look at in this photograph is where we see the horizon in relation to everything else that's in the photograph. And of course here we have this tent in the foreground, and we can see that we are indeed higher than the tent. And we can see just how much higher we are by where we see the horizon. That, indeed, as we looked at with the curvature calculator, is at our eye level. It's the horizon is apparently at the same height as us, at our horizontal line of sight, at our eye level or height above the surface. And there it is, and it's higher than the top of the tent, or appears to be. We know this isn't a bulge. The sea isn't rising up higher than the tent. We know that we are actually higher than the surface. And we could measure this in various ways and say, oh, we're 300 meters above the surface of the water. Yet, we see a horizon that is also 300 meters above the surface below us, right? But this is what happens in our eyes. This is what tells us our height in relation to everything else. Here's another good example of exactly that. You can see that we are quite high above this container ship, and looking down, yes, we look down towards this container ship to see the top of it. But where do we see the horizon? We see the horizon at a height above the container ship that is relative to our height above it. It indicates, it's telling us that we are indeed higher up in the sky or above the surface than the top or the bridge of this container ship. And the horizon tells us that. And so we see everything, we see the surface beyond the ship. And you know that if you brought your height down, or lowered your eye level if you like, then this horizon would come down with you, and eventually it would be that the ship would appear to be on top of the surface. So let's have a look at that. Here we have a photograph of obviously a container that's in front of us, a container ship that's in front of us. We have other container ships. This one's further away, this one's further away, and there's another one even further away. And they are all on the horizon. And of course we have quite a low view. Our eye level, or our height above the surface, is not very much. We're somewhere around here. Yeah, the hull of the ship there, around that red line, something like that, maybe even lower. And so we have a very close horizon. And this ship is just in front of it. This one is still just in front of it. This one is sitting on the horizon, and so is this one further away. It's still on the horizon. This horizon is not curvature, is it? The ship's not suddenly going down. I think there's a bridge over there or something by the looks of it. Yeah. Nothing's going down just because it's beyond the horizon. Your horizon is closer if you are lower to the surface, and so everything else that's further away than the distance you can see effectively to the horizon will just appear to sit on the horizon. Or it will eventually get obscured by all the other things going on the surface, in the air, just above the surface. Visibility isn't infinite. Here's a series of pictures that have been used in an attempt to debunk flat Earth. And they do make some accurate observations of what we're seeing, but don't understand how they are falsely attributing this to a model that it doesn't fit with. So, for example, you look at the top picture here. It's not very clear, I don't know why, but first picture taken from 200 plus meters of elevation. Horizon is significantly above the ship. Okay, so what you're going to see is a horizon that is at that person's eye level. So it might appear to be at this height of 200 meters plus. Second picture of the same ship taken at 100 meters. So they've halved their elevation. They've come down 100 meters, and the horizon is directly behind the ship. Well, yes. What's this telling us? This horizon here is telling us our height in relation to the object, the ship. So we are indeed higher up than the ship. We're not quite as high up as the tops of the masts. We're about as high as the bridge there. And we can see that because that's where the horizon is. The horizon tells us. So the horizon has moved down with us. It's gone from appearing to be at 200 meters and down to our 100 meter eye level or elevation. And now we have this third picture taken at just a few meters above sea level. Much of the ship is lost in surface clutter. Yes, that's very true. The horizon has become very close, as happens whenever we look across the surface like this. And because the ship is further away than where we see this apparent horizon, or we see mirroring starting and all sorts of diffraction, refraction, lots going on, then of course it is obscured. But the horizon is, so are they trying to say that this line here is curvature, and now the ship is suddenly below curvature that wasn't existent in the pictures above, the first picture of a higher elevation? Where's the curvature here? Why is the horizon coming up with our eye level and not somewhere below the ship? And so I didn't finish reading that, but it's possible to discern the upper works and that there's a reflective mirage in place. Hull is definitely behind the horizon. Well, yes, the hull is definitely obscured. And again, remember that we're looking at something, it's zoomed in, and the angular size of the ship is very, very small compared to everything in front of us, between us and the ship, however far that distance is. If we are 1 meter above the surface, then we're still going to see, 4 or 5 miles? I can't remember exactly how far it should be. But, and then, so we've got a good few miles of surface that we can see across until everything that's going on the surface disrupts our view. That's the limit of any clarity that we're going to get because of our height. But remember that the model talks about a fixed geometric shape, but the horizon is moving with us. And it does depend on our height, yes. But here it's suddenly passed off as curvature, just because you get so low that everything on the surface and just above the surface starts to obscure your view of something much further away and apparently much smaller. That's passed off as curvature, and all of a sudden this ship looks like it's dropped off an edge. Yeah? So they've done some messing around in the last picture. Same picture with the second picture partially overlaid for comparison. Even with vertical stretching, it's possible to see that the hull is behind the horizon. Yeah. Okay, but do you see what I'm saying? It's automatically assumed that this is evidence of curvature when it's optical distortion. Just like we have the barrel distortion, we have this kind of distortion going on across the surface that really distorts the light entering our eyes from whatever is off in the distance. Yeah. So if we now go back to pictures of ships, again, it's very obvious here that the horizon we see in the distance tells us our height relative to the ship in the foreground. We can see from all the other aspects of this photograph that we are indeed higher than the bow here, but we're not quite as high as the top of the ship. And if we did rise up and go higher, then we know that the horizon would also appear to rise up with us. And so the fact that the horizon does this, depending on where we're looking, indicates that the horizon is not a fixed geometric shape. And again, it's the geometry of perspective, or the geometry that you can use to describe perspective, that has been converted into a spherical model of the Earth. Now, another thing to point out here is that, yes, the horizon is at eye level, and if you look horizontally at eye level, then you will see the horizon right there. But it doesn't matter whether the camera is tilting up or down, or whether the horizon is on the upper or lower part of the photograph. It might have been cropped or whatever. It doesn't matter. What you have to understand is that it's the horizon's relationship or apparent position compared to everything else that we are seeing in our personal point of view, our perspective at any given place or time. So again, the line here, whether we tilt up or down, we tilt the camera up or down, the horizon line will remain in the same place relative to the ship. It will stay, it will stay there, but it might go up or down in our field of view depending on how much tilt. But its relationship with whatever's in the foreground will remain the same to continue to tell us that this is your height compared to the object that you see in the foreground. And one more to illustrate this. I actually got this from a tweet by Keith Truther. I did ask permission, but I didn't get a reply, but I hope you don't mind. I presume this was taken from a hotel balcony. I saw some other shots from the balcony, and we can see here exactly what I'm talking about, where we have a cruise ship, and this time we're looking at it from this side-on perspective, this side-on point of view. And we see the horizon up there at the same height, relative height, as the chimney or the funnel on the ship there. So we can kind of estimate from this photograph that Keith was on a balcony at about the same height as this funnel here, and thus we have the horizon appearing to be at the same height. And again, you know that if you went down to the beach and you took this photograph, you would see the ship appearing to sit on the horizon, or maybe a very small increase of extra space from the ship up to the horizon. Yeah. So we're not looking down. So if we go back to those models and we keep all those points in mind, we'll see that none of this fits with the modeling of a globe Earth. So back at the curvature calculator, we can think about what we've just seen and what you can go out and test for yourself anytime, anywhere, how we see reality, and see that this doesn't represent it at all. We talked about angular size, and of course the fact that the further something away is, the smaller it appears to be. So even a massive ship will appear to be very small on the surface a very long way away, and a small wave or fluctuation in temperature and distortion in the air just above the surface or on the surface will obscure our view of the boat. So this model, remember, is one of these so-called scientific or mathematical models with a 2D representation and everything in proportion. Again, proportion can be anything because we're dealing with circles and geometry. This is the way they can work their magic. The math magic is because you can assume all sorts of radiuses and things like that and make it fit on a circle. But everything is the same height. So when again, this was specifically to talk about what is hidden in the distance. So if this was a mast or a ship or something in the distance, this green line is representing what we would see, and this represents what is cut off. Well, in reality, what's cut off, how much of what we see of a distant object is cut off, because how small does that object appear to be because it's further away from us, the observer? Well, it's tiny, but of course this has just remained the same relative height or the angles that are used and things like that relative to the model itself. It's not a representation of how we see the world in reality, yet they are trying to tell us this is a representation of reality when it's not. There's no compensation for angular size or the difference in angular size over distance, none of that. And as I said before, the geometry of perspective, the way you can describe what we see in terms of geometry, has just been flipped and turned into this fixed surface. So here they have us looking down to a horizon. Now, if something is on the surface and we are above it, then of course we look down to it, just as we saw with those photographs of looking down on ships. but the horizon was above the ship. So let's say that something, let's put where they're saying this green spot that crosses for the horizon. Let's say we can see a ship at that location on the surface, and we're this height above the surface. Well, where is the horizon going to be? It's going to be at our height. It's going to appear at our eye level, our horizontal line of sight along this eye level. So not down here, not on the surface. Yeah, it's completely wrong. So another thing to think about again is this side-on view. Here we have this side-on view as if we can see the surface and we see nothing beyond this two-dimensional line, just this line. Whereas any view that we have, it doesn't matter which way we look, we are going to see a horizon at our eye level. Here's a very crude side-on orthographic view illustrating what an observer might be seeing. I'll just bring up this picture again to show you what we're representing here. This is the photograph of a ship taken from a height that was obviously higher than most of the ship, and we can see the horizon there in the background coming up higher than most of the ship. That's how it looks in reality. We can also see this apparent convergence. The clouds go off into the distance and they become the horizon as well, as does the surface. Everything appears to converge at this midway point at what we call our eye level, or it appears to be that way. So this is what we're trying to represent with this illustration here. I'll just turn that off, just keep that in mind. Okay. So compared to the Earth curve calculator, is this a more accurate representation of reality? Well, in some ways yes, and in some ways no. Remember, they had us looking down to the surface on a curved surface. Obviously you would have to do that. Here we are looking straight ahead, which we commonly do, but we don't see this apparent convergence. There is no difference in angular size. Of course, it's way out of scale, but we can still again talk about the kind of angles that we might see, or what we see appearing to happen. So if we, for example, put this line in here, what we can see there, if we do the same as what we are told is we do when we look at the horizon on the outside of a globe with the Metabunk model there, the idea is that they have us looking down to the surface, but that's wrong. First of all, you don't look down, and even if you bring up arguments of dip or something like that, look at where the observer ends up seeing a point on the surface compared to the boat. This point on the surface, even and especially if that surface was curving down and away from us, would appear lower than the ship itself. But that's not what happens, is it? Let's bring up that photograph again. The horizon is higher than the back of the boat. So first of all, we're not looking, the surface is not curved, and we're not looking down any imaginary curve whatsoever. We are looking straight ahead. This is a picture of reality at the top, and down here I'm trying to at least represent how it appears to us. So no, we're not looking down as is assumed in the model. So what we have here is we're going to have angles, and those are the angles that get converted from this level surface into a spherical surface. But of course there's also something missing here. Let me just take off that line. And so with this horizon here, this convergence beyond the boat and at the same height as the funnels, how can we represent that? Well, the way to do that would be to do it like this. Oh, this looks totally weird, doesn't it? But this is again representing what we see, or how perspective works. And so now we have this angle here that brings the surface up to the eye level, apparent eye level. So this slope here is merely representing this apparent elevation of the horizon that we see when we look forwards, and we're representing it in the side on view. Of course, if I start to represent what we see as if I was a real observer looking at this scene, then of course I'd have to bring the blue up to all of this red line, because this horizon's always going to be at our eye level. So we've detached ourselves from reality. We've created some kind of model. But what we end up with here is something that represents how we see reality and how we see level surfaces. You go and compare this to looking across a level surface, and that's always what happens, the way we see the world. So this represents the way we see the world, and you could put the same angles and distances and elevation in. Of course, it's going to be a bit more tricky because you're not using geometry anymore. You're dealing more with right angles and things, rather than the radius and the portions of a circle. But basically, that's what has happened. We've got models of a spherical Earth that do not fit reality, and we have reality screaming at us that the Earth and the water on it is indeed level all the way. Thank you very much.